Thursday evening. We are finishing up multivariate functions today, which means we're finishing up the valley of the Grand Canyon. Because after this, it's the first cliff basin that we have to climb up to. We've been looking at partial derivatives up to this point. Well, actually, a partial derivative is a special type of directional derivative. Right. The idea behind a directional derivative is you're on a surface. Right, you're at a specific point. Point in a direction. What's the rate of change in that direction? That's a directional derivative. Right, so clearly the partials would give you the directions along the respective axes. But those are not the only directions. Even when you're looking at just standard Calc 1, you would have studying the plane, you would theoretically have an infinite number of directions you would take the derivative in. Now, typically, when you look at Calc 1, what you're looking at is a rate of change with respect to something. So you don't really need a direction for that. Right? So we have two, again, we define it for two variant, but this can be extended to any number of variables. So we have a two-variant function, has domain D. Let AB be some point in our domain and define U as cosine theta sine theta. The directional derivative of f in the direction of U is given by that limit. And notice in this case, unlike with the partials, we're allowing both variables to vary. Provided this limit exists, of course. Okay. All well and good if we want to know what a directional derivative actually is, but not particularly practical if we want to find a directional derivative. So there's the actual value for a directional derivative. That's how you calculate it. Partial of f with respect to x at your point times cosine of theta plus partial of y at your point, or partial of f with respect to y at your point times sine of theta. Also, keep in mind that while we are defining u as cosine of theta sine of theta, it doesn't have to be in that form. As long as it's a unit vector, it would be in the form of cosine of theta sine of theta, right? It's just theta wouldn't necessarily be a known angle. Favorite operator is next. It's called the del operator. Now it's just an operator, right? So it operates on something. uses that we study in this course for the del operator. We look at one now. We look at the other two towards the end of the semester. And the first use is what's known as the gradient. So the gradient of f, del f, is a vector whose first component is the partial of the function with respect to x, and whose second component is the partial of f with respect to y. This is if we're dealing with two variables. It's just a natural extension to multiple. I actually do consider the three variable, the del operator, the three-dimensional del operator. But it's a very natural extension into any number of dimensions. That is sometimes also written as just grad f. Yet that is not the del symbol, right? It's called a nabla. And here's typically how we would see it. So I'm going to write it out for the two dimensions. Now again, it is an operator, which means by itself it makes no sense. This is why we write it like this. So it'd be this. And then you can kind of think of it like scalar multiplication for vectors, even though that's not really what we're doing. Properties of the gradient. If the gradient of a function at a point is the zero vector, then the directional derivative of f at that point is 0 in every direction. So if you have 0 gradient, then you have 0 rate of change in every single direction. If the gradient is non-zero, then your directional derivative is maximized when u points in the same direction as the gradient. In other words, the gradient represents the direction of maximum change. And that maximum change has value as the norm of the gradient. Finally, directional derivative is minimized when u points in the opposite direction of the gradient. So the negative gradient would represent the direction of minimum change. And the value of that minimum change is the negative of the norm. And then 3 dimensions. Right, what we use a lot in physics also, you have to deal with time. But then we deal with what's known as tensors. I hate tensors. You have a book on tensor calculus. And more than that.
Something else to look forward to.
Only if you go to grad school.
All right, well, maybe not.
Tensor calculus is not an undergrad topic.
Maybe not.
Even though you need tensors in general relativity, which you can take in undergrad. As far as I'm aware, tensor calculus is a grad topic.
I'll take your word for it.
Remember, I showed you at the beginning of the semester the Einstein field equation. Those are tensors. Each one was essentially a 4x4 matrix, which means that field equation is 16 separate equations. Four because there are 4 dimensions that we look at: time and 3 spatial in general relativity. So now imagine doing tensors in string theory. 10 by 10 matrix, so 100 equations time in the 9 spatial. No. With gradients, we can rewrite the directional derivative as simply del f dot u, and that is the form that I will be using. First thing, let's find the gradient. So what's the partial with respect to x? What's the partial with respect to y? Evaluate that at the 0.72. -14, -24. Right, or factor out the 2. Fix something. Let's call it u sub 1 to represent the direction for the positive, or 45 degrees from the positive x. What would that be?
Cosine 45.
Where's 53 coming from?
The hypotenuse between 7 and 2.
Do you need that for direction?
I'm clearly mistaken.
If you're multiplying by 53, it's no longer a unit vector. And it has to be unit.
Okay, that's right. U is a unit vector.
It's supposed to be root 2 over 2, right? Root 2 over 2. So our directional derivative, or our rate of change, is the gradient dotted with our direction vector. Two times a half is 1. That's nice. 7 root 2 minus 12 root 2 is what? There's the rate of change in that direction from that point. All right, so very important, there are two things you need for a rate of change. You need the point, and you need a direction. Saying this.
Yes.
That one.
Yeah, I'm just thinking. When it says 45 degrees from the negative x-axis, how do you know if that's 45 degrees above it or below? That's the question, isn't it?
You take that to be above. Why did you change slides? So it'd be that.
So normally, when it's when we're just going from the positive x-axis and we're rotating counterclockwise. But when we have a situation like this where they're saying off of the negative axis, we don't rotate counterclockwise by default. We take that to mean
No, because the positive would mean above.
oh,
That's why we take counterclockwise, because
Oh.
that's above
okay,
the
I
positive
see.
x-axis. So when you go to the negative now, it's
Right, I see.
just like if I were to say 45 degrees from the positive y-axis,
Right,
it would be that.
positive. Okay.
Because if you going to the right,
Right.
as the positive direction. So negative root 2 over 2, root 2 over 2 is our direction vector. The gradient's the same. Now, the direction vector is different. What is the rate of change now? That's all there is to directional derivatives, honestly. The important thing to remember is that your direction has to be represented by a unit vector. That's a mistake. Should be 60 degrees from the negative. Look, you're spreading it. Find del Z. What's the gradient at the point then? Become a 1. For the first part, 30 degrees from the positive x. What's the unit vector? gradient dot u. What's our rate of change? Vector for the direction for the second part. Gradient dot direction. So what is our rate of change? I need a refill. Do that while I go refill. before you plug in the value of the function.
Negative 128x over x squared plus y squared plus 2. Comma. Negative 128y over x squared plus y squared plus 2.
That.
Yes. Infinity squared plus the whole term.
Oh, should they?
Yes.
Why are they squared? Well, it's not really that good of an explanation.
Because you had to use the chain rule. The chain rule we learned back in Calc 2, I think, on all that business in the parentheses. Right?
Okay, but is the chain rule reason why it's squared?
Well, no, but in doing the chain rule, you go from you go to negative 2 exponent.
That's not from the chain rule.
Well, before you get to the chain
That's from the
rule,
power rule.
before you get right,
Power rule.
the power rule. One of those.
Derivative of x to the n and x to the n minus 1. And the power is minus 1. All right, so then evaluated at the point, you get what?
Got negative 128 over 49 and negative 256 over 49.
Can we factor anything out?
Factor out a negative 128 over 49.
And what are you left with?
1, comma 2.
I agree, I like that better. What did you get for your direction? Might be easier to write that way. But then we're going to have this dot product, right? And what do you get as your rate of change?
Negative 64 over 49 times 1 plus 2 root 3.
Times what?
1 plus 2 root 3.
Someone second that? physics are you taking? What physics are you taking? So you've taken E and M? Electric potential. If that doesn't bring back nightmares, you didn't truly take E and M. What type of? Oh, whatever. I'm not an English major. Just for that, when we start to get to electric flux, I'm going to make you derive it. And I think I will require you to use the relativistic effects as well. Because you're a physics major. Let's wait till you take E and M too. And so we're given the equation for electrical potential. We want to find the rate of change at the point 3,4 in the direction towards the point 2,6. Two ways to go about this. We want to take the path of least resistance. So we're going to go the easy way. Rewrite V. That's not incorrect, but that's not what I'm looking for.
ln of x squared plus y squared over 2.
Where's the over 2?
Well, one of the properties of natural log is that if you're raising what you're taking the natural log up to a power, you can multiply the natural log of that power instead of raising the thing in the natural log to the power, right?
That's why I was asking where the over 2 was. If
Okay,
it was inside
yes.
the log or outside the log.
Yes, outside, right there.
Right, so you're dividing the entire log by 2, not taking the log of something divided by 2. That's what I was trying to get at. Yeah, write it that way, because that's going to be easier to differentiate than the original. Now use that to find the gradient of the nightmares. Of course, in physics, it would be this. But that's a different story. We'll get to that later. It should be simple with the rewritten form.
One half outside the effective, 2
2x over ln x squared plus y squared ln 2y over ln x squared plus y.
First off, simplify. You don't need the 1/2 and the 2's. No. What's the derivative of natural log of x?
So why do you still have ln? Good question.
Only you know the answer to that.
X over x squared plus y squared y over x squared plus y squared.
So there is our gradient. Oh, we'll be studying that again later after multiple integration. We'll see that again for sure. X over r squared, y over r squared. At our point, what's our gradient? I'm going to do it this way. This is another common notation. Keep in mind, it's not technically a vector divided by 25. It's 1/25 times the vector. This is just how we write it. What is our direction vector?
Unit vector -1, 2.
Unit vector of -1, 2?
Of vector -1, 2.
So your semantics are off. Right? It's unit vector in the direction of -1, 2. Right, but yes, what is that? What is that unit vector?
-1 over root 5, comma 2 over root 5. You can factor out the 1 over root 5.
Which I'll do. But first, I want to ask, how did you determine -1, 2?
So we start at 0.34 and then we move towards 0.26. So that's how you get that vector.
So it's the vector with initial 0.34 and terminal 0.1 or 26, right?
Yes.
And then I will factor out that. I wanted to emphasize that because it happens every single semester where they take that to be the direction. Not realizing, oh, we're starting at a point and we're going towards that point as the direction.
So I guess it wouldn't be normal to be interested in, like, instead of 3, 4, the origin. But if
You could.
if you were, then it would just be.
then that would be.
Right. I see.
But yeah, there's no rule that says we can't be at the origin, right?
Yeah.
It'd be like saying that you can stand anywhere on the circle except right in the center. What do we get? Maybe what would be 1 over 25 root 5, right? And then times One over 5 root 5. Or if you're so inclined, root 5 or 25, right? Doesn't matter. They're the same thing. You could, but we won't, but we typically will not write that. It's not incorrect, it's just we don't really ever write a constant to a fractional exponent, generally speaking. Find the gradient of f. Agree? Seconds. That's all this slight nod. Evaluate at that point, what do you get? Agree? Now comes the fun part. We're going along that curve, specifically in the direction of increasing z. Well, increasing tells us we want a derivative. So let's take our prime of t. What do you get? What is it?
1, 1, 2, t.
But we're at that point. 1, -2, 1, right? So for that point to be on the curve, what does t have to be? It's obvious. It's 1. First coordinate of r is t, and the point's 1, so t has to be 1. Then you just verify 1 squared is 1, so the z coordinate works, and then 1 minus 3 is -2, and the y coordinate works. So that point is indeed on the curve. Yay! Defined r prime at 1.
Could you go over that logic again? I didn't get it.
So we want the point on that curve, right? The curve r. So what does t have to be at that point? It has to be 1. Look at the first coordinate.
First coordinate of r.
Compared to the first coordinate of the point.
Okay.
T and 1. Right away tells you t has to equal 1, right?
Why do we look at the first coordinate of r?
Because the first coordinate in r was t,
Okay.
which makes it really easy to determine what t has to be.
Okay. But what about like if we were to take the second coordinate of r?
Then you set that equal to -2.
Okay. Thanks.
But that's why I said then just check to make sure. With t being 1, does it satisfy all 3 coordinates? 1 squared is 1, so that's good, and then 1 minus 3 is -2, that works.
Okay.
112. Is z increasing in that direction? Yes, it's positive. We take that as our direction. 112. But is that vector good to use? So what do we take for our u? We're going to get 1/6 times 5 plus 8, right? So 13/6. Again, or 13√6/6. Look at this one first.
Consider the Fontino.
Yes! It's a new word that I made up. Oh, never mind. I can't do that one first. So first I want you to find the gradient of f, then evaluate it at the point. Determine the direction. And finally determine the rate of change in that direction. That's 4 things you have to find. While you're doing that, is there anyone who didn't get their exam back? Anyone else? Your name? Anyone else have things? We have 2 casualties. This is not bad, 2 out of 20. It's only 10%. Here we find gradient. What's the gradient function? What is it at the point? Do we have a direction yet? And what did you get for the rate of change? Did we have a rate of change? I agree. Tino is a new particle, like the neutrino. Hmm? Push on the who's turn. Who discovered the neutrino? It doesn't really interest me that much because the particle doesn't interact with that world at all.
John Neutrino. John Neutrino. That's exactly what I was saying.
28 points from the final score.
For that?
Yep.
Dang. I think we should up the crowd.
You're right, I think we should up it. Unfortunately, it's not going to be 50, though. There's a reason I chose 28. $496 points off from the final score. Again, not arbitrarily chosen. If you can determine why that's the number that I chose, then I will revoke that and you will not lose points. Without looking it up. While you do that, while you take that, so consider that same function. Direction of maximum and minimum increase.
Aren't 28 and 496 perfect numbers?
I said here. Fine. Yours is revoked, but it's now going on to you. So 496 points off of you. But yes, that's why 496 is the 3-digit perfect number. What's a perfect number?
Subtle factors is the number. Not including the numbers.
Not including the number itself. Yeah. So sum of all the factors less than the number. Is there a 4-digit perfect number?
It's like 8,000 something. 8120.
Yep, 8128.
Maximum is like from up there.
There's actually a formula for it, I believe. There is. Sort of. Oh, well. Not really a formula, but they all fit a certain form. Yeah, the next perfect number is 33,550,336. Perfect numbers are awesome. So yeah, it's completely useless knowledge too. Like perfect numbers, what's the importance of perfect number? There is none. Completely useless, but that's what makes math sexy. So what's the direction of maximum increase? From the previous function.
U is equal to, at the same point,
At the same point.
U is equal to 2, -4, -8.
Well, that's not U.
That's true. That's the direction.
Yeah, the direction would be. And how'd you determine that?
The maximum is when the direction is pointed the same as del of the function. So I took the del of the function at the point.
What about minimum?
-2, 4, 8.
And how'd you get that?
The minimum is when it's in the opposite of the del of the function, so you would just take the previous answer and multiply it by 1.
Something from the judge that well. What are the values? Not simplified. You're not incorrect. It's just not simplified. Two root 21. How'd you get it?
I just simplified 84, root 84.
So how'd you get root 84?
That I don't know. I'm missing some stuff here.
What's the minimum increase? So be careful when you say opposite. There are two meanings for opposite. You could either have the additive inverse or the multiplicative inverse as opposite. Questions on directional derivative? Easy, right? Too bad that's the last easy thing we do all semester. I will tell you, multiple integration is very, very difficult. And it's not the actual evaluation that's difficult, it's setup. The setup is extremely difficult.
Is it like a lot of setups, or just the way you have to write it?
Not how you write it, it's how you determine how you're integrating. It involves a lot of visualization. It's easier with technology. But you don't have access to a 3D graphing utility for a test.
I have almost 10 years of practice with Origami. I think I'm going to be
So
okay.
at that point, it then depends on how nice am I going to include a picture for you or not. Once you get the setup, multiple integration is very easy. It's setup that's extremely difficult. So you should be putting the finishing touches on your project. That's due tonight. It's not going to get extended again, so that's it. 2 homeworks are coming up.
So you're missing homework 10.
Homework 10 was, oh, that's right, it's due tonight. I accidentally erased it. Homework 10 is due tonight. Then you have 2 more coming up. As I said, next week we start multiple. We look at the double and the triple, and that's all we look at in this course. But you can have a lot more than that. You can have like a 26 variate function, in which case you're taking a 26 level integral. We only look at 2 and 3, and that's hard enough. But we start with the simplest type of region for a double integral, rectangular region.
I think I know what you're talking about. I can take a picture.
So that's where we start Tuesday. Actually, all next week is double integrals.
The other one was just the little boxes.
Have a good weekend.
I think